like to do this like this. So, for beginning, I'm Jean-Jacques. I'm from France, so sorry if my English is poor. So actually, I'm working for proprietary software on an hypervisor, but my first love is for open source software. So my first job, I had to replace a part of the operating system called Lepton and put an open source kernel on it to do some fancy stuff. So I just explain you later. So I just give you a context. So sometimes in French government they work, and in 2013 they sent a paper that say embedded is important for Europe, and we have to do something to independence, and they bring the term softwareization. So softwareization can be defined that the founder provides chips with more functionality, like Ethernet, like crypto, like everything like that you can find before on an MCU, but you can find in a bigger processor. And user with the availability of things like Android or like iPhone want some fancy things, just GUI, just touch things, command your device with the voice or with gesture. And the second part is I don't know if there is what kind of relationship between softwareization and Internet of Things, but there is a correlation. So for me, IoT is the integration of all things in one network. So the thing can be the tiny sensor, the gateway that get back the data from the tiny sensor, and the cloud that can make some fancy thing like I don't know, data mining to make some decision later. And for me, I just put an image of the gold rush in the United States, because for me IoT is that nobody know how we can make data, but everybody sells some useless thing, funny things. So it's the new Eldorado for me. So in this kind of thing, this kind of tiny sensor, that's this map, I think. So you see there are a lot of proprietary software developed, like Signal, like CMS, like Threadix. And this tiny thing provides just simple things like task synchronization, task load, but nothing else. And as you can see, the required memory, internal memory for that is less than 20 kilobytes of RAM. And after, if you have more RAM, you can put some better system with more functionality like echoes or like airtime or base rods or robots. But again, you don't have the functionality like a POSIX operating system can have to VFork or to do exec or whatever you want. So we are just here. So with the same constraint of RAM, you can provide more fancy thing with POSIX API. And if you have more RAM, megabyte of RAM, you can take Linux, you can take BSD, or you can take a proprietary software if you want. So what we bring in Lepton is just POSIX functionality over a kernel like FreeRTOS or like echoes. So we provide the POSIX interface with the real-time and thread extension. What this funny thing and really powerful thing that called streams. For example, if you have an USB device, the low level can be a driver, for example, /dev/USB something, and you have the profile, the USB profile that is device driver 2. So for example, if you have mass storage device, you can put mass storage device over the low level USB and you create another device that can be the real device for mass storage device that you can move on the PC. We provide the BSD socket interface for network application, so you can do open, listen, and things like that, and bring, for example, a little tiny web server. For other projects, we put the NanoX over it, so we can. So we put NanoX over it, so you can have some fancy things for GUI or things like that with button, toolbox, or whatever you want. And to have a kind of, you know, in industry, people like to keep their things because they think secret is important for us, so for them. So in this kind of thing, we have to find a license that you can open the core of the operating system when people can make the contribution, and have a license that permit people to keep their things secret if you want. So the FI license with a special linking exception will choose. And after that, the real purpose of Lepton is, for me, is portability, because for me, you can take, for example, a library on Linux on FreeBSD and just recompile it and put it on Lepton if you want to use it. So for me, it's for me the real purpose. And after that, in embedded system, for sensor, reliability is very important. So if we can have something that is proof or that don't crash too much, it can be really, really useful. And after that, we can see that application become complex, and for me, we have to keep the system unstable because in this tiny target, we need to have we have to retrieve everything. So that's it. Global architecture of Lepton. So as you can see, we have above the hardware, and we can support ARM7, ARM9. And what we do is only the POSIX layer and all over this mechanism to integrate these three kind of kernel. So you have Sega, that's the proprietary kernel, but it's the support of Lepton. And the two new version is the ECOS version and the FreeRTOS version. So we take this kernel, we just use the basic mechanism, for example, task creation, semaphore, whatever you want. We wrap a bit with kernel mechanism, and we provide a POSIX layer with V4, exec, whatever you want. And on top of it, you can create your process, your pseudo process, because you don't have virtual memory, so the address space is the same, but it's a kind of process because you can have the same semantics, and you can do V4 exec, and in this thread, in this process, you can create thread with special thread or whatever you want. So that is the global architecture of Lepton. And how can we build our firmware? So for the firmware is really simple. As you can see in the demo, you have a configuration file when you put your targets, whatever you want, what kind of process, how many stacks you want, do you want file system, whatever you want, do you want to mount something in the beginning of the system. We have a little parser that creates C and .C and .H file, for example, for the tiny rootfs. And this tiny rootfs can be used after for mounting something that's on flash or in SD card, for example. And after that, we have the Lepton structure that is in Git. We use cons not makefile to build our firmware. And after that, you have your F. And you can use, for example, OpenOCD and GDB for the debugging or for the flashing. So, in a Lepton firmware, the basic component that is embedded is the kernel. For example, ECOS or FreeRTOS. And all of the components is depending of your application. For example, if you want I don't know, web server, you need LWIP and Mongoose, for example. I put a cube on it because we pour TinyGL for some fancy things and to see if it match. We develop a little FTP server, and we can, as you see, we have a little GUI stack with NanoX that act as a X server, a tiny X server. And we can put on top of that a tiny version of FOSDEM, that's the toolkit on Linux. But there is FLNX, that's the toolkit that bring all the functionality of FOSDEM on NanoX. So it works. And right now it's just the demo time. So let's say for example for the I just show you a configuration file for this kind of board. So it's at the Cortex M0 with 32 kilobytes of RAM and 128 kilobytes of flash, and we just put Lepton in, and I just show you the configuration file for example. So the XML configuration file that I talk about earlier, that describes, for example, the maximum of process you have in the process table, maximum open file that to have file descriptor, and other things like, for example, the site. And after that, if you go down, you see we can add some peripherals that can be /dev or whatever you want to the file system. And after that, so that is device driver that is general, that is independent from the platform. And after that, we have the peripheral that is dependent from the platform. For example, we have on UART, and we have some fancy LED examples that is our hello world in embedded system. And after that, you have your init process that can be launched after the kernel starts, and the init process at the input and output on the serial port. And after that, you have all the pseudo binaries that will store in the file system for execution. So, for example, you see the stack and you see the priority. So, I don't know if you have some time to make the build process right now, but I just make a demo. So well, we have this line. This is the tiny binaries that parse the XML file to generate what we want. So as you can see, it parses the file and it creates the binary for the target. For example, we can find init in /sbin, whatever you want. And create the device driver for us. And now we have to just to put this generated file on the global project file and compile it to generate the firmware. So as I say, we use cons. And we use this kind of line. So on the opti file in the Python file, you can find all the option to build the firmware. So for example, if you want NanoX, if you want WIP, if you want whatever you want. And we can precise what core do we use. Do we use a FreeRTOS core or do we use an ECOS core? So for the Cortex M0, the FreeRTOS is much tiny, so it's more appropriate for the firmware. So and after that, we just launch the companion. So as you say, it's still warning, but we need your help. And that's it. We have the firmware, and if we go in .bin, we have the elf. So for example, if we want to see the size of this elf, to see what is the size of this firmware. So as can you see, the text is under 100 kilobytes, so you have some place around to do whatever you want. BSS, so the initial stack is 1K for the starting, but when I show you the demo, there is on the 32 bytes of RAM there is around 12 or 30 kilobytes of RAM available for your application. So I don't click the test file because it's going to take time and it's really interesting to see the second demo too. So the board is connected. I think it's this. So if I start, I just have a little tiny shell, like a Unix system. So we can make the round, just see what it is inside there. And as you can see, we have TTY S3, that's the output console, and we have a tiny LED devices. Just for example, if we go in Lesbin, for example, there's nothing on Lesbin. Yes. So we have all the binaries that we configure and we link in the platform. So that's it. And I just want to show you a little example of code For example, for blink LED, so it's just a little blink LED example, but the real thing is the code to do that. It's really simple, and it's like on Linux. You just open your LED devices file and just write on it and sleep. And after that you close. But the funny part is the driver part. As you can see, this is the driver part of the LED. So you have just a structure with points of function that is managed by the VFS and that make the abstraction. And when you open the LED, you just call the functions that configure the GPIO, and that's it. Then after that, when you want to write something, you just check the side of the buffer, and after this you just do the ping pong between the two. So it's really simple. So I bring a second demo more complex with that it's the Cortex M4 from 3 scale, that's a K60 board with SD card, with Ethernet, and we don't use external memory. So these boards have 128 kilobytes of memory, and we put a web like Mongoose on it. So I just do the connection. And this board uses the ECOS profile. So the kernel is it. The microkernel used here is FreeRTOS, and the microkernel used here is ECOS. But we have the same base of code to implement the target. So I don't have the time to show you the second demo, but I'm open for questions if you want.
We have time for one question.
How would this integrate in a tool chain? Say I want to use binaries from which provider on the desktop for these devices.
Yeah.
So this one needs to generate C code and then one H, and I see that my binary this is okay. So my computer. Would that be possible? Am I clear?
Yeah. For example, if you take an object code from generated from Clang, for example, is it possible to put on it? Yeah, it's our next step, because I don't show the future of the Lepton, but for me we have to use Clang, for example, because you have a better intermediate representation, and it can be really useful if people use Clang and test it to build Lepton. So it's interesting for us.
Okay. Okay, thank you very much.